Right. Hello, everyone. I'm going to talk about the probability of collisions as it relates to Wi-Fi. Now, statisticians have predicted that lineups form at theme parks as you wait for a ride on your favorite roller coaster because there's a variability on when people arrive in those lines. If everyone was scheduled at specific times to arrive in a very linear fashion, we wouldn't have lineups and these long queues waiting to get on our rides. Now, you'd think that these theme parks, knowing that there's long lines, might build additional capacity into their rides. But again, statisticians tell those theme park designers and creators that even if they added more capacity to their theme parks, to the roller coaster rides, it still wouldn't alleviate the problem because of this unpredictability in when people arrive to go on their rides. My name is Troy Martin. And as part of my introduction for myself, I just want to talk about the last book that I've read, right? It's a book written by Greg Ennis called Beyond Everywhere, the story how Wi-Fi became one of the most successful technologies that we know today. And if you scan this QR code, it'll take you to amazon.ca, where you can order this book for yourself to read. It's a riveting tale of the origins of the Wi-Fi standard. It talks about the highs and the lows as we jostled, or different companies jostled to get their features and their expectations incorporated into the protocol itself, which is one of the reasons we have many options within our 802.11 standard, is just to get everyone in agreement to move the standard forward. We let in a bunch of these different features and functions that wanted to be included. Now, if we just step back and put a different perspective on Wi-Fi, if we imagine being in our universe, which is hundreds of thousands of light years across, right? There's a lot of empty space in our universe. And if you think of celestial bodies, almost like frames hurtling through space, there's a lot of gaps in time or gaps in distance between those objects. In fact, our nearest star, Alpha Centauri, almost 4.2 light years away from us. Our nearest galaxy, the Andromeda Galaxy, we're looking at about 2.5 light years away. So there's a lot of gaps between things in our universe. And if we think about that space between all these objects, planets, stars, asteroid belts, if we think about that as the gaps in between our frames that we transmit, one thing that we may want to think about is what can we reference as kind of a standard unit of time, right, to calculate the distance between these objects. We could think of transmit opportunities and measure the number of transmit ops that we have in between transmissions. Or maybe we want to use time units, right? Even the name sounds like it could be a good candidate for something like this. We have standard things like beacon intervals, which are 100 time units, right? Or maybe slot times is a better reference. If we calculate the distance between things in terms of slot times, we could use that. Now, to keep going down this theme of space and time, I'd like to introduce the concept of the space airtime domain, right, which is partly inspired by Einstein and his space-time domain to visualize things. And to make Wi-Fi people feel a little more at home, I've introduced some spectrum captures where we can visualize the amount of time that frames take to consume or airtime that's consumed as they transmit, and we can see lots of gaps in between these transmissions. Now, different places in our Wi-Fi universe will be more active, right? So we can have denser transmissions, but overall, there's a lot of gaps in between all of our frame transmissions. And we run into this problem that we have related to medium contention. And Greg Ennis in his book goes into great detail explaining the layer 8 battles between those who wanted to have medium contention or who wanted time-based access to the medium. So again, I highly recommend checking out that book. But what I have on the slide here is a slightly different perspective of describing medium contention. Because we are talking about celestial bodies orbiting around different solar systems, I've created 4 bubbles around our primary goal, the goal of transmitting a Wi-Fi frame. Now, in order for us to transmit that Wi-Fi frame, we have to clear all the conditions around that. And this is where the probability comes into play. If you look at a voice frame, for example, that buffers up audio signals every 20 milliseconds to let that transmit, even when we have a queue queued up and ready to transmit, we still have to avoid collisions in Wi-Fi. So we engage in this random probability to avoid two transmitters talking at the same time, and we roll a dice, right? So we pick a random number, which gives us our variability in how transmissions line up at the theme park ready to take their ride, right? We also want to make sure that no one else is talking. So we do a check to make sure that we don't hear raw RF energy out in the environment. And we also check to see if there's another Wi-Fi transmitter. In fact, Wi-Fi is extremely polite and extremely sensitive to other Wi-Fi transmitters, that it's 100 times more sensitive to another Wi-Fi transmitter than it is to other non-Wi-Fi related wireless transmissions. We also wait gaps in time, right, to make it fair and equal for everybody. At the end of the most recent transmission, everybody waits a fixed amount of time before counting down this random number that they've rolled on the dice. After that gap in time, based on slot times, we start counting down towards 0 for our right to transmit. And Wi-Fi I like to describe as an overly polite protocol, right? It'd rather have someone else transmit than take the initiative itself and go through transmissions. So one way of thinking about Wi-Fi, it's like having a giant dance-off, right? Waiting for someone else to transmit first. You go first. No, you go first. So if we relate this back to voice, we have the sequence of all the gaps in time and the periods that we'd wait for a voice transmission to take place. And to make this more interesting, I threw up some time intervals, right? So in the scheme of Wi-Fi, we're looking at time in microseconds, right? In space, we're measuring distance in light years, but in Wi-Fi, it's microseconds here. And in this frame, for a voice packet to be delivered using the codec G711, we're looking at roughly 300 microseconds for it to hurl through the space, right? And then we have gaps where there's emptiness, no one else talking, which is filling up that space between our bodies. Now, because we're talking about probability, I just want to take a moment to talk about distribution curves and the normal distribution curve, which I'm going to overlay on a direct sequence spread spectrum trace to make everyone feel a little more comfortable. So if we draw some probabilities on top of this, we can try to calculate what are the odds of two frames being sent at the same time and resulting in a collision, okay? Now, means are useful when we talk about normal distributions, but if you have the skewed distribution, that may be where you want to introduce a median, right? So we had interference from a microwave, it's a little more skewed, it's wideband interference, but it tends to lean to one side over the other, right? But that's not really what happens when we roll a dice. And when we roll a dice, it's more of a uniform distribution curve, right? Where we have a 1 in 16th chance of picking a random number and avoiding what someone else is selecting so that we don't talk at the same time, counting down to 0 for that green light to access the airwaves. Okay. And that's relatively simple before we introduce QoS. But we want to rig the game a little bit in sort of a sense. So when we introduce QoS to Wi-Fi, we want to give a slight advantage to traffic marked in a higher category. So for our voice or video related traffic, we want them to count down to 0 or win the right to transmit just a little bit earlier. And here I've also attached a token frame capture where you can pull from the beacon information, just where these timers come into play, that we're giving preferential treatment to voice and video to be able to transmit faster. We're not outright starving any of the background or best effort queues. We don't have a priority queue that any voice traffic comes in, it always wins. It all comes down to probability and likelihood of being able to transmit. So once we introduce QoS and we look at the time that it takes to transmit that frame across the airwaves, because that contention window period is reduced, because we don't have to wait as long, with QoS enabled, that voice frame now hurtling through space only takes about 190 microseconds of airtime, right? Leaving a lot more time for other frames to sneak in and achieve their transmit opportunities. Now, for reference, if we compare the difference between a QoS and a non-QoS frame and the amount of airtime that can take, we can see the numbers here. And in the contention window numbers that I've displayed, it's a worst case of the dice roll. So rolling the largest number that you could, either a 15 on a 16-sided dice or picking a number 0 through 15, or picking a 3 on a dice that has, between 0 and 3 sides. Right? Now, to come up with those calculations on the airtime that a frame would take, I used Gearman's Wi-Fi airtime calculator tool. So I just wanted to give a shout out to Gearman's, who I'm sure is watching online or the next chance that he can. If you scan this QR code, it'll take you directly to his website where you can download a spreadsheet that allows you to play with a bunch of calculations for various frame sizes, QoS settings, and data rates, right? So if you get a chance, I highly recommend checking out his calculator tool that he's provided to the community. Now, with all these calculations that come into play, and we try to analyze the probability of two frames colliding, we leverage something called the Markov chain model, right? Which is a model based on stochastic probabilities, where the probability of an event occurring is based on the state of all the events that you're in at the moment. So as we transition from one event to another, the likelihood of things happening keeps evolving and changing, right? So if I simplify this a little bit and draw out the model, if we were in a sunny state, knowing that we're in that sunny state, there's a certain probability of us remaining in a sunny state, so tomorrow being sunny, or having it be cloudy or rainy the next day, right? And if we move into a cloudy state, all the probability matrices change, right? And if we expand this out to Wi-Fi, it becomes even more complex, right? Because we have to look at a whole bunch of different factors, right? What comes into play is, what is the airtime utilization at that moment? How many frames are in the queue from other wireless transmitters waiting to be transmitted? How far are we from the access point? What's our SNR? Frames will take longer to transmit as we move further away from the access point if we're in motion, walking up and down a hallway. So all these different parameters change from moment to moment, and so these Markov chain models become incredibly more complex. You throw in QoS, and we have different timers for different types of frames that now need to be transmitted by various transmitters. We heard yesterday, Cisco was talking about Wi-Fi 7 and multi-link optimization and the different QoS standards that we have there, preamble puncturing, right? So now this takes it to a whole new level, the complexity that's involved in calculating the probability or the likelihood of two Wi-Fi or multiple Wi-Fi devices colliding when they go to transmit. So when we think about the efficiency of the Wi-Fi protocol and improvements that we're making, I'd like to suggest that we consider efficiency as a measurement of the gaps in time, a reduction in the gaps in time between sending frames. So if we can lower the transmission opportunities, which reduces latency and jitter in our application data that we're trying to send, that is an overall measure of the improvement or an increase in efficiency of our wireless protocols. And on one last note, I just wanted to remind everyone that when it comes to Wi-Fi design, it's ultimately a blend of artistic merit and the science that goes into everything that's Wi-Fi related. Thank you.